that we are talking about limits, we have different kinds of discontinuity. And the first kind of discontinuity is, or at least that we talk about, is jump discontinuity. So this is practice problem 3 from jump discontinuity and the limits of piecewise functions. The only instances really where you're going to get those jump discontinuities are certain functions that have asymptotes, but then also you're going to have piecewise defined functions. That happens a lot. That's a common application, especially on the AP exam. So here is the question. We always want to first graph, especially if we're given the explicit description of the function. And graphing will help us get a better sense of visually what's going on. So although you could do this completely analytically, and analytically means you solve the problem simply using the algebra and you don't rely on any visual aids, the visual aids are very helpful. So when you think about this, we have two pieces. So 1 minus x squared, that's a parabola. The minus sign out front of the x squared means that it's going to be opening downwards. And the 1 is a vertical shift. In other words, we're going to raise the entire parabola up by 1. And we're not moving it horizontally. This is the only thing that we're changing is the vertical shift and then flipping it upside down. So we have the regular x squared graph, flipped upside down, and raised up by 1. So here's what that would look like on this side. And then as I do this, the left side, I'm going to note that we don't want this doesn't count for when x is equal to minus 1. At x equals minus 1, there's going to be something else. So here would be, as I come down, here's x is equal to minus 1. So we're not including x equals minus 1 here. So I'll put an open circle to denote that that's not what's going on. And then the parabola will continue down after that. And then the next part is at x equals minus 1. The way we're filling it in is we have the value 2. So this is the value 1. This is happening at minus 1. And this right here, this height is 1. So here would be 2. And that means at x is equal to minus 1, the function value jumps up to here. So this is really what our graph looks like. We've got, there's our x-axis, there's our y-axis. We've got a parabola with a hole at x is equal to minus 1. And in where that hole should have been, instead the function value is defined to be some separate value up here. It's kind of a dot. It's like we removed a point, a singular point from this parabola and shifted it to some other function value. So what that means is that the function is still defined. We have a definition for where we're going to assign x is equal to minus 1. And the way we would say that is h of minus 1 is equal to 2. So we have a definition for the function at x equals minus 1. It's just not obeying the rule defined by this parabola here. So with that being said, we kind of set the backdrop here. Let's turn to these limits. So part A wants the limit as x is going to 0 for the function. So x is 0. Well, that's just here. So we're actually completely disregarding the hole that we put into the parabola entirely. And so notice that really from here, I'm going to put this in blue. All of this is continuous. So the blue is continuous. There are no discontinuities. We haven't put a hole in it. It's just a parabola. It's just a polynomial. Polynomials are continuous. So everything in here that's blue, also this would be considered continuous. The limit, whenever you have continuity, that means the limit is going to be what the function value is. So in this case, the limit as x approaches 0, as we approach 0 from both sides, so here's x equals 0. As we approach it from both sides, we can approach it from the left, and we're approaching this value right here. If we approach it from the right, we also approach the same value. We're approaching what the function value should be, and we are approaching h of 0. So, oops, I made a mistake here. It should be the limit as x approaches 0 of h of x this is equal to h of 0. The reason for this is because it's continuous. And h of 0 is 1 minus 0 squared. And I'm getting that from here. And that's just 1. So the graph, it looks like it's going to approach 1. It's what it's going to be. So there's different ways you could do this. You could look at the graph. You could say it's approaching 1 from the left and the right. So the limit as x approaches 0 is going to be 1. Or you could do it analytically. You could write this out. You could say, okay, polynomials are continuous. So since we're not at the trouble spot, we're at x equals 0. We're trying to get to x equals 0. That is not a trouble spot. We haven't placed a hole at x equals 0. We put the hole at x equals -1. So we'll address that later. But for part A, don't overcomplicate it. It's pretty straightforward. All you're going to do is recognize, okay, well, we're in the interval where I am continuous on just a quadratic. So it's just going to be the function value at that particular point that I'm approaching. So how do we handle part B then? Is we have that the limit as x approaches -1, and remember now -1 is the trouble spot. That is where we are introducing, I'll put this in orange, our discontinuity. So let's see if that affects anything. Now remember that the condition, we can't just plug in the function value like we did here because we see that it is not continuous. But just because it's not continuous, that doesn't mean the limit fails to exist. It's possible to have the limit exist, but not have it be continuous. And this is going to be one of those cases where the limit does exist. It's just not continuous because the limit doesn't correspond to what the function value should be. So what do I mean by that? The way we check to see if a limit exists or not, and the test for that is to say whether the left-hand limit, so x approaches generically, I'll put a, from the left of a function, this needs to be the same thing as approaching that point from the right. You need to approach it from both directions and reach the same exact limiting value. And so we can apply that here. And in order to show that this limit exists, we just simply need to show this above. We need to show that even though it's not continuous, if I'm approaching it from the left versus approaching it from the right, I'm still approaching the same exact thing. So x approaches -1. We're going to approach it from the left. That's what the little minus sign means, of h of x. And when we do that, we see that we are from the left coming up the function here, and we're approaching the y value of 0. So we are not going to equal 0, but we are approaching the y value of 0. And then, okay, what happens if we approach from the other side? So x goes to -1, but this time from the right. What are we approaching? Well, if I'm approaching the x value -1 from the right, I'd be coming down and approaching, well, I'd still be approaching as if I were going to hit the x-axis. In other words, a y value of 0. And so we see that the limit, the left-handed limit, approaches the same thing as the right-handed limit. And since they approach the same exact thing, this shows that this limit exists and it equals 0. Now, this does not again show that it is continuous. In order for it to be continuous, h of -1 would also have to be 0. It is not. In this case, we have moved it up to the value 2. And so it's not continuous, but this limit exists. Both limits exist, but only one of them is continuous. The one in blue, this is the limit exists and is continuous. And in part B, the limit exists, however, it fails to be continuous. And that's actually a precursor and foreshadows something we call removable discontinuity, which we will address in the following lessons about factoring limits and rationalizing limits.